Ladies and gentlemen, we introduced Po-Shen Loh before. He is the co-founder of XP and the leader of the USA IMO team, among many other things. And as he said before, he was a contestant once, and he won many competitions. Today, he is our guest speaker. Without further ado, please welcome Professor Po-Shen Loh.
Wow, thanks everyone for coming. So today I want to talk about probability. So suppose I'm thinking about what kind of phones to buy. You know, I was polling the audience, like iPhone or Android, iOS or Android. And suppose I want to say with 50% chance I want to pick an iPhone. How would you make this decision? If you really just wanted to have 50% chance of picking an iPhone? Possible? Ah, great. Thanks, Cody, for lending the coin. So, as you know, if you flip a coin, the probability that it's a heads is
51%.
In a math class, we say it's 50%. Of course, you know, strictly speaking, it's not 50%. Part of the reason why it's not 50% is because you can tell when it lands whether it was heads or tails. Although if you weighted it carefully, you could possibly get 50% out of this. Okay, so I can do this at 50% with a coin. Suppose, on the other hand, I have a different thing. Maybe I really like iPhone for some reason. And I want to pick an iPhone with probability 3/4 and Android with probability 1/4. And I still have this wonderful mathematical coin which has 50-50 chance of being heads or tails. How might I use this to make my decision? Yeah?
You flip it twice, in which if it lands to, say, heads, then you choose the iPhone or the Android. If it lands at least one tails, then you choose iPhone.
So the proposal was to say, to get a 1/4 probability of success, I simply flip the coin twice. And if I get tails, tails, is that what you said? Then I say that way. And that happens with probability 1/4. We know that also.
And you only need 1/4.
And I only need 1/4. This is pretty good, you know? Maybe I only have a quarter, or you know what? I can do this with a penny. So, okay. Although it doesn't cost you the quarter, you can give it back to Cody at the end. So it's all fine. But now suppose you work out, maybe you're a little bit different though. It's not like you had a 3/4, 1/4. Maybe you want the iPhone with probability 2/3. I heard. Okay. Well, what am I really asking? What I'm asking is I'm saying, I got this coin here, and I want to generate an event which is successful with probability 1/3. I see a hand. Before I take the hand, I just want to talk a little bit about why maybe it's quiet. If you already know the answer, if you know that you've seen this entire problem before, I will actually request don't give it away for the audience, because it's more fun to discover it together, and I'll have a harder version for you in a second anyway. But before we dwell onto that thing and even giving the harder version, why is 1/3 not giving an instant answer like the previous one? What's wrong with 1/3?
Because it's not out of the power of 2.
Okay. So again, what are we trying to do? We're trying to get a probability of 1/3 using a coin. And here's an observation that it appears to be hard because you're saying something about power of 2. What is not a power of 2? What is a power of 2? The thing, the denominator, the 3, that's right. Hard. Apparently hard is because the denominator is not a power of 2. Okay. Suppose I ask you something like 3/8. Is this easy? Yeah, because you just toss it 3 times and you choose 3 of the outcomes. Very good. And that's good because 8 is a power of 2. All right. Actually, with this whole system, like well, the denominator being not a power of 2, a lot of these things are like tossed 3 times, right? And let's even analyze sort of what was that thought process there. The thought process that was going through people's heads is if you had an algorithm, I mean the algorithm you were using to generate this probability 1/3 event, if your algorithm said something like toss coin some number of times, right? And then make a list of successful outcomes. And then check if the result is in The list, what this algorithm always gives you, I think many people made this observation, this algorithm always gives you that the probability of success is equal to something over 2 to the power, the number of times that you found. The number of successful. So it seems like we've just proven that you can't do it with a coin. So one thing I'm going to say is, if you have seen this before, I'll give you a challenge problem. And we'll go back to this challenge problem later, so that you'll always have something to think about. Here's a challenge problem. Get probability of success equal to, this is like a calculus beat, right? So, do I want arctan? Why not? Arctan 3/4 divided by pi. What's that? It's okay. So this is like challenge fashion. If you've already seen this before, try to do that. We'll do 1/3 first. Okay. Quick question: how many people have already seen how to do 1/3? Okay. Not that many. So this is going to be fun. Have you seen how to do that? Okay. Then you have something to think about. I always like to have some challenge problem ready, because then at least, even if you're ahead, you can still be banging away at something. But let's do this together. Have I just disproved it? Have I just said it can't be done? What did I actually prove? I mean, in some sense, there's a positive statement that came out of here. Yeah. Right.
You can rewrite the probability as some fraction with the denominator as a power of 2. You have the algorithm for generating and make your probability that fraction.
So your statement was, whenever I'm trying to get a probability something over power of 2, I can do it this way. That's correct. Unfortunately, I don't have the power of 2 in the denominator. But this thing proved something. It actually proves my algorithm can't look like this. Does that make sense? So we've got to think outside the box. But isn't this like what every algorithm is? This is why math is fun. Math is all about getting the creative juices going. How to think outside this box we have here? It's not pretty general. Have you seen the question before? Oh, good. So that you have an algorithm that you'd like to propose. By the way, it's okay if you just have an idea and not an algorithm, because if you just crowdsource a bunch of ideas, eventually they kind of polish into something. So here's an idea. It might actually already work, but let's try.
So you toss the coin until you get a head.
You toss the coin, not some number of times, right? He's saying toss the coin until you get a head. Is this something I can do? I think so. But if it takes forever, we'll address that later. Okay, don't worry. Let's keep going.
And
now what?
If you get an odd number of tails, then
Okay.
it's a success.
So what you want to do is you want to check the number of tails that you've got along the way. So if the number of tails is odd, then you're saying it's success. And if the number of tails is even, I guess that's the other one, then it's a failure, which means the opposite of success. Okay? Let's see. Can anyone help me analyze this thing? See how this thing might or might not work. And I want to emphasize, don't be afraid of giving something that might not work, because you can always build on top of it. So, yes. Isn't this something for statistics? It could be. Geometric distributions, yes, indeed. What you were saying about the geometric distribution, does somebody else know this before I say it? Does anyone know what he's talking about with the word geometric distribution? So, yes.
So that's basically when you keep doing something until you get
Good. Then what is distributed geometrically?
the probabilities of how many times you
Good. Number of times. Right? So the number of times that this coin toss has is this geometric distribution. You're right. It's actually nice that you use the word geometric, because we're actually going to analyze this thing using something else that has the word geometric in it. Somebody said the word geometric series. Why do I have a geometric series? What should I actually be doing right now if I'm trying to check whether this actually works with 1/3 probability of success? What should I do? Yeah. calculate it. So you want to calculate the probability of success, right? How do you calculate it? You make a list of the things that work, right? So what are the things that work? So what works? What works meaning success? Oops. I'll write the success list. Successful outcomes are, you could either get, what's the shortest successful outcome? One. Yes, meaning T and then H. Is this okay? I'm writing the outcomes as like the list of points. Okay, people follow? What's the next successful outcome? TH, 3. Is that okay? Next successful outcome. And so on. What is the probability of each one? What's the probability that you get a T first and then an H second? 1/4. Right? And then this guy's probability, 1/16. This is 1/64. There's a geometric series here. Right? If I want to add this geometric series, how do I add the geometric series 1/4 plus 1/4 squared? And so on. How do you do this? Yeah.
Take the first term, divide by 1 minus the ratio.
So he said take the first term divided by 1 minus the common ratio. And this works out to 1/3. Hooray. So it works. Well done. Good invention. I'm impressed that you came up with that so fast, actually.
Why isn't the probability that you succeed 1/2? Because you either have an odd number or an even number, and after each one you have 1/2 chance to fail.
So actually, so the question was, wait, but why isn't the chance 1/2? Because you either have an odd or even, and every time you have a half chance of failing. Yes.
When you think of even, the 0, like having 0 counts as even. So you
Yes.
have an extra.
Yes. So you have an advantage. It's because the ones that count, actually the easiest way to see it is to look at this, because we can actually make a list of all the different outcomes, right? These are the successful outcomes. What are the failed outcomes? Failed outcomes are H, TTH, and so on. And if you look at all the probabilities, the probability of the H alone is actually 1/2. So you actually have a balance, a bias. And the reason the bias happens is because 0 is more likely than the other ones. Does that make sense? It's sort of like saying, you can't actually just use the number of outcomes and say there's one successful outcome out of 2 outcomes, because they're not equally likely, so to speak. There will be something along the lines of what you are saying, though, in this talk. Don't worry, you will answer something too. Good. So we have this procedure now. This is wonderful. Now you can always decide whether or not to have to decide something with probability 1/3. Yeah.
I'd also like to propose an alternate method.
Okay. We'll actually need an alternate method. And I'll say why we need an alternate method. It's because I don't know which geometric series adds up to that. Is that okay? Okay, and by the way, the beautiful thing about math in some sense is that there are many ways to do things. And actually what mathematics really is about is in finding all the different ways to do things and learning that they are connected to each other. So you have an alternate method. Maybe let's go back here.
I was going to suggest you consider them in groups of 3.
In groups of 3. Okay, let me just erase this. Hang on, I'm just going to get some space. So now what you want to do is you want to consider in groups of 3. You mean like the first 3 flips,
Yes.
and then the next 3 flips. Okay?
Well, first you flip only 3 times. And
Groups?
3. Yeah.
Okay? So what you do is you're saying the procedure. First step, flip 3 times.
Yes. And then if there's 3 heads or 3 tails, you disregard those and flip again.
Okay.
And if there's
So let's make a list, right? So the first thing you said is if it's 3 heads or 3 tails, then each of these is you disregard, and then you flip again. So I'll just write that. Disregard, and then you flip again. Meaning that you go back up to here. Okay.
And if there's 2 heads or 1 head, then
So heads or one head?
If you have two heads, then that
Yeah.
means you have one tail, and you look at the index of the tail.
Okay, so I'm going to write this down, okay? Because I want everyone to follow. Don't worry, we'll let this idea come through first. And what I'd like to do is I'd like to crowdsource the solution. And we might refine it along the way. But I want to let you have a chance to write down your idea. What you're saying is you might have two heads, right? And if it's two heads,
yes.
you look at the place where the tail is.
Yes.
Are you okay? There are three places for the tail. Okay, two heads. Then there are three positions for the tail.
And then whichever one you determined in the beginning, which I probably should have said.
Determine it now.
Yeah.
So which one?
The first one.
First one, okay. So there are these three positions for the tail. If the tail happens to be first, then you're going to say
Then it's a success.
success.
If it's second or third, it's a failure.
And if the tail is the second or third, then you say it's a failure. Okay.
In the case of two heads, or in the case of two tails, you do the same thing for the one head.
Okay. And in the other case, it's like so you have either three heads, no heads, two heads, or one head, so to
In the
speak.
case you consider the position of the head.
You use the position of the head, and if it's the head is first, is that okay? Then you success, you win. And if the H is not first, then you fail. Sorry, it's all cramped together. But does this make sense what he's proposing?
Yeah.
Yes.
So this is pretty much the same thing, but just a little bit simpler. With
All right.
coins,
It's with what?
2 points.
2 coins. Okay.
So I mean two
And
flips.
2 flips, right?
So if you have 2 tails, you flip again.
Just a second. Let me clear this so that we have the space. So you said if you have, this is still fun. Okay. So what you want to say here is that we're now going to take just 4. We flip 2 times. Okay. And now if you have, is it 2 H's?
Two tails you disregard. 2
Okay.
heads is a success, and a heads and a tails is a failure.
So 2 tails is a disregard. And you flip again.
It's the same idea, just a little consolidated.
Very good. Then you go up to there. Okay. And on the other hand, you said which one do you want to do something?
Tails, heads, or heads, tails.
This is failure.
Yeah. And then heads is a success.
Good. Heads is now success. Okay. And in this one you disregard and flip again. Here's a question. Both of these are similar in the sense that there's some disregard and flip again. And also, now this is where what you said is relevant, is that at the moment that you stop, right, at the moment that you don't flip again,
Yes.
you exit. And out of these exits, like this one's easier to see, out of these exits, 2 of them are fail, 1 of them is success, so there's a 1/3 chance that you succeed. Did that argument make sense? And the reason is because there's a symmetry. The symmetry is that at the moment of exiting, it could have been any of these 3. If you're not comfortable with the symmetry argument, you can actually analyze it in the exact same way as over there. I mean, you could write down the list of ways in which you could succeed. Indeed, what is the list of ways you could succeed in this particular algorithm? It's HH, 1/4 chance. What's the next way to succeed in this algorithm? TTHH, 1/16. Next way is TTTTHH. Does this make sense? Wonderful. So we have just come up with 2 different algorithms. Well, almost like 3, but these 2 are similar, which will give us the 1/3. At this point, you can even do other fractions. At this point, you can do stuff like 4/7. You can do all these wonderful rational numbers, right? How would I do 4/7? Yeah.
Choose
3 flips.
and choose 1 set to disregard.
1 of them you throw away, you have 7 left.
Choose 4 success.
4 of them you success. It's nice, right?
So it's like binary.
Sort of. Okay, you said the word binary. Very good. If you've seen this stuff before, don't give it away. But if you have something to say.
Can we do this in a necessarily bounded algorithm?
Oh, okay. So there was this question about how long this takes. Let's go there first before we go on to this funny irrational number. Okay. Right now we've gotten every rational number, but there's this deep question of what if I go forever? Okay. Hopefully that bothers you because But in our algorithm, you could go forever. So let's now go here and study what's the probability that we do go forever. I see. So if I move them out, that might work. Yes. Okay. Yes. Good. And the reason moving the mouse works is because then it projects a black screen. Okay. So let's see. So now we need to study what is the probability that I go forever. I mean, if the probability that I go forever is like a 10, this is very bad because I could end up flipping forever with some reasonable chance. How can I analyze this? Yes.
It's 0 because it's a half times to the infinity.
You're saying it's half to the infinity.
1 over
okay?
2 to the, yeah.
So that's morally correct. You have something to say here? Yes? Okay. So I could that's 1/2 to the infinity.
That equals almost never.
That-
Not necessarily 0.
You're saying that's almost never, but not necessarily 0. Okay? So, yeah.
Would it be like 1 minus the
Okay, now here's the word limit. Uh-huh.
geometric series approaches.
Okay, so I heard the word limit, I heard the word geometric series. I mean, I'm just getting ideas and then we'll discuss this together, yeah?
Well, if you think about the probability that it does end, then if it ends first, like if you flip a head, that's 1/2 and ends. If you flip a tail, then a head, that's 1/4 and ends.
Okay.
If you keep doing that, and you add all them up, that's 1/2 plus 1/4 plus 1/8.
Wow. Okay, I like all these ideas. I'm actually going to talk about both of these steps that just came up. Okay? But you had something to say too.
Did we not already find 1/3 and 2/3?
Okay, so what you're saying is that you can also work this out and see that there's a 1/3 chance of succeeding, a 2/3 chance of failing, and all the probabilities add to 1. Right? And therefore it must end. Okay? So that's also good. What I want to do is I will talk about 2 of the ideas that came here, and then we'll also analyze one more thing, which is that, even if you know for sure that it's going to end with probability 1, you would also like to know that it ends before dinner. You might like to know it ends fast. Okay, so we'll also analyze that. Okay? So one approach to this probability go forever, somebody said that, it's sort of like taking 1/2 to the power of infinity. Because, this is a good way to start thinking about this. That why the 1/2? Because you go forever exactly when? When do you go forever? What does the point flipping sequence look like?
When you get 2 t's.
You just get like tail, right? The idea is that you go forever. The probability you go forever is exactly the same as the probability that you get just t's. Okay? And you said that, well, there's infinitely many of these, and you take 1/2 to the infinity, that's 0. Okay? And that's a good way to start thinking about it. I'll just say another way that you can think about this if you want to be slightly more rigorous. Going forever, I mean, actually even more rigorous is more fancy, but I can say here, the probability you get all of these things, here's something that maybe is easier for you guys to immediately understand. So this probability is less than or equal to the probability that you get t. I'm not saying what happens after that. Is that okay? Just the first 6 in a row are tails. What's the probability of first 6 in a row is tails? I'm just doing it through like 1/2 to 6, right? Okay. Well, so whatever this probability is, it happens to be inside the step. Okay, but what's special about 6? Nothing. So somehow if I had not just 6, but 600, it's also, this probability is less than or equal to 1/2 to the 600. Actually, strictly speaking, what's going on here is I have a bunch of finite events, and this thing here is the intersection of all those finite events. So that's actually what's going on here. And then the probability that you end up here is the limit of all of these. And if you take 1/2 to the finite number, and the finite number gets bigger and bigger, you get 0. Is this okay? So actually the probability that you go forever is actually 0, which you might say, but I know a way to get that. But at the same time, the probability is actually 0. Just like, here's a fun experiment. I like to do this with people too. It's like, hey, give me a random number between 0 and 1. Great! Point 2 is a rational number. So the probability that you get a rational number when you pick a random number between 0 and 1 is, why is it 0?
Well, because essentially a rational number always has to it has to have like a finite. If you could basically have a random string of numbers instead, like any random string.
Right.
The probability is a rational number instead of that random string. That's right. Because a rational number has to have some order to the string.
That's true, but that only proves it's less. There's a key word that I want to pick. Yeah.
If you put it in binary and it's fractional, it has to just have a whole lot of zeros at the end.
Okay, there's another key word that's relevant. Yeah.
Cardinality.
Yeah, it's called countable.
Accidental parts.
Yeah, so somehow the number of real numbers is uncountable. The number of rational numbers is countable, and the probability of each individual rational number is 0. And if you take a countable union of probability 0 events, it's still probability 0. Actually, that's kind of interesting, though. We just witnessed a miracle. Isn't that amazing? Like random number between 0 and 1, the probability of that being rational is 0. You're good. Actually, that gets on something else. In some sense, I mean, this shows that somehow our human brains are very good at creating certain probability 0 events. Actually, that's why, I mean, my particular area of research in mathematics is called combinatorics. I work on something called probabilistic combinatorics, where we use something called the probabilistic method to sometimes to construct objects that are very hard to construct as humans. Because in fact, suppose I wanted to ask you, please construct for me a number. Tell me a number between 0 and 1 that is not rational, that's not algebraic, meaning it's not like the root of an algebraic equation, has nothing to do with e and has nothing to do with pi. I mean, yes, you can do it, yeah. Okay, yeah. So again, you've just listed another famous thing. Okay. Yeah. Right. So you're naming another famous transcendental type number, right? But what I'm trying to say is that it's actually not easy to construct these things, and that's actually why. So in my area of research, we use probability to say, even though we can't construct these things, we'll prove that it exists with probability 1, actually. I mean, we prove that if I do a random experiment, it happens with probability 1. And then we circumvent this issue of like when we try to generate something, we get probability 0 objects. Okay, but that was an aside. So indeed, this was something here. And maybe I won't dwell on the other approach. But so this is like probability 0 that you will go forever, which is nice. But suppose I want to know something about how long it goes. Okay? In statistics, there are more things that you might use to analyze the distribution of a random variable. But the very first thing that you can analyze is the random variable is how many flips does it take before I get my first h. Right? Suppose I want to look at that. Let's put this here. How many flips before the first h? Right? That's a number. That's a number 0, 1, 2, 3, 4, and so on. That's what's called a random variable because the outcome depends on this experiment. Anyone who has taken statistics, what sort of property of a random variable might you care about here? Yeah?
Expected value.
The expected value. Okay. The expected value is sort of like saying the average. It's a weighted average in some sense. So what we're studying here is, I guess Q is different from question mark. But we want to know what's the expected number of flips. Before first h. And I guess when I say this, so just to know what the grammar means, when I'm saying before first h, maybe it's that, as I'm flipping it, that's a flip, right? So if I just flip and I get an h, what's the number of flips I made before my first h? I flipped before the first h. It's 1. Is that okay? That's all I want to say. It's like, maybe this is like that's not what, I didn't want to emphasize on the grammar, but I just want to have something very precise to talk about. So again, if I flip it and I get an h, the answer here is 1. So now, how do you calculate these expected values? What do you need to do? Yeah?
You do the number of times you want to, or wait, hold on.
Okay.
You do the 1 over the probability.
Okay. So you're going into the fact that it's a geometric random variable.
Yeah.
Let's pretend we didn't know that statistics. I want to do this from bare hands. Okay? So Roger, yeah.
So you sum over the number of flips times its probability.
Good. So let's make a chart, right? So there's a chart, meaning the number of flips before the first h. Okay? That's one side of my chart. And you also have over here a mouse pointer. Well, actually you have here the probability that this happens. Okay? So the number of flips before your first h, as we said, the smallest this could ever be is 1, right? And by the way, that's just getting h, right? What's the probability that happens? 1/2. 1/2. Suppose it's 2. What outcome does that look like? th. And what's the probability of that? Okay. Suppose it's 3. The probability of this is 1/8. Okay. So now I have numbers of possible outcomes of my random variable. I've got probabilities of each one. What should I do with this information? Actually, I have a question. How many people here already kind of know expected value stuff? Some, no, okay. How many of you know what a weighted average is? Many more. The basic idea is that you don't just want to average the numbers 1, 2, 3, 4, 5 up to infinity because the answer is infinity. So actually it's hard to define what that average means. But that's actually a different question. But we want to weight it. We want to say this guy's worth more than that guy. And when you do a weighted average, what property does the weight vector have to satisfy? If you do any weighted average, yeah. The sum of the weight has to be 1, is it? Yes. This is a geometric series, okay? So now what we do is the expected value is equal to the weighted average, which is exactly equal to 1/2 times 1. I'll do it this way. I'll write 1 times 1/2 plus 2 times 1/4 plus 3 times 1/8 and so on. How do I do this? Is that a geometric series? No, that's not a geometric series. Oh, it's space underneath. This is weird. What's that? Does it converge? That's another good question. Okay, hopefully it does, because now we have some ideas. Yes? It's 2. How did you get 2? You can do it with polylogarithms, or you can do it with sigmas. Does anyone understand what you just meant? I mean, you got the answer. Very good. I'm just trying to go through something that we can talk about together. Yeah?
It's like the expected value of the number of times that also we're going to get in the head.
It sure is. I agree.
But then that's obviously 2, because if you flip a coin 2 times, you will check one head.
I'm not entirely sure that that's actually going to be approved. I mean, in some sense, sometimes when the numbers are small enough, you can actually get these to work. This is actually a straightforward sum in some sense. Let's go back there, yeah. Multiply the sum by 1/2. So what you're saying is, assume the sum converges, then if the sum is s, which is equal to 1 times 1/2, plus 2 times 1/4, plus 3 times 1/8, and so on. Is this a trick that you guys learned in school? No? Yes, maybe? Doesn't matter. So what you're saying is, let's multiply the sum by 1/2. Now you get 1 times 1/4 plus 2 times 1/8 plus 3 times 1/16 plus and so on. And now what?
Subtract them.
Somebody's saying subtract them. Okay? So assuming that these sums converge, I'm just going to assume that sums equal up. Then you subtract them, and what's left? 1 times 1/2. How many 1/4s are there? 1 times 1/4 plus 1 times 1/8 and so on. Okay? Which we know what is this? This is geometric. This is equal to 1, so somebody got the sum is equal to 2. Right? And this is good. Actually, I usually like to share another approach, just because, especially because this is called Calc B. There's actually something here that you can use calculus to do as well. Oh wow, people know this already. Yeah, yeah.
You could make it like function.
Make a function, okay.
Maybe like
over 2 to the n. And what do you want to do? So is that f of n?
Yeah.
Are you suggesting f of n to be 1 over 2 to the n? N over 2 to the n.
Yeah.
Okay, okay. You're saying f of n is n over 2 to the n. Okay, let's do this. Because that is what we're doing. And then what do you want to do?
And then limitize n approaching.
So if you look at the limit, and by the way, whenever I teach, there's no such thing as a wrong answer. I actually teach the Putnam class at Carnegie Mellon University, and this is exactly how we do it. We want all the ideas because then we can put them together. The limit as n goes to infinity, f of n, actually, this one is going to 0. Does that make sense? Because of the fact that the exponential grows so much faster. Okay? So, that's not quite. I was saying there's some calculus somewhere here, yeah?
You want the summation of
Okay. You also use another approach, and it's okay, let's just put everything here. You want a summation from something to infinity. I equals, no, actually, I is a bad choice for this. I mean, I don't know why, I don't want to use I, because I is also the square root of I is 1. So k equals 1 to infinity of f, yeah, okay.
Or, yeah.
Yeah, doesn't matter.
Yeah.
Okay, now what do you want to do? I agree, that's exactly what you're looking for. Okay. Oh,
You break it up.
you break it up. How do you break it up? Oh, these are ideas. Okay, good. You're saying break it up. Okay, this is something. Remember, calculus somehow, I want to get a derivative here somehow, actually. That's where I'm going here. There's going to be something with a derivative in here. Yeah. You can use the curly thing to approximate it. I like that. You mean the integral. yes. So what you're saying is that this thing is like what is this thing anyway? This thing is going to be some Riemann sum, right? This is some Riemann sum. This is the area underneath a particular curve, and the integral is close to it. So that is true. That will let you approximate. But I actually want to get an exact answer, and I want to do something that uses a derivative somehow. Yeah.
How about g of x?
Oh, g. So there's a new idea. Okay, so you're going to just, for fun, define a new function, g of x. So g's going to let g of x equal
X over 2
x over 2
plus x squared over 2 squared
x squared over 2 squared
plus
x cubed over 2 cubed, and so on. Okay. Actually, can someone else tell me why you might care about g of x? Yeah. G of x is a geometric series. Okay, this is a geometric sum. X over 2. X over 2 all squared. X over 2 all cubed. So it's a geometric sum. Then I know what it is. It's going to be x over 2 divided by 1 minus x over 2. Okay. Did I make a mistake? It's okay? Yeah, okay.
Because
You want to find g prime of 1. So let's see. What is g prime of x? Okay. If I let that happen, then g prime of x is going to be equal to, well, let's see. When I take this derivative, I get 1/2. When I do this one, what's the derivative of this? 2x over 2 squared. You see what's going on with this derivative? This is nice. And then over here, this becomes 3x squared over 2 cubed. And this thing over here becomes 4x cubed over 2 to the 4th, and so on. Okay. Well, while this is true, now you actually care very much about g prime evaluated at 1. Because if I plug in 1 here, isn't that exactly what I want? Okay. So what I have here. Okay. So let's do this. What? I'm sorry. G of x is this horrible thing right there. Okay? So what I have here is that if I take g prime of 1, that's going to be exactly the sum I want. Maybe I should write it, well, I can write it this way. This is exactly equal to the sum I want. Okay? Not factorial. Actually, it is 2 factorial is 2. Anyway, never mind. So how do I take g prime of x, right? So to do this, well, g of x was that horrible thing. I guess this is Calc B. We can do this. So if we want to write that down, this is not a divide by sign, so now two of them. Okay, g of x is equal to, can we simplify that thing? It's like x.
X over 2 minus x.
Yikes. Okay, what is it? What is this? All right, guys. What is this thing?
Oh, use the
2 minus x y plus x over
Remove this plus x.
minus negative x.
Yes. Minus of negative x. Okay. Over.
Over x minus 2 squared.
Okay, I'll do this one. Is it okay?
Yep.
Did I make a mistake or is this okay? What did I do? I think I should. We tried to use the quotient rule, right? Like that guy right there, derivative of this, minus derivative.
Wait.
Yeah.
That's right.
Yeah, that's right. Because this is like x times minus 1, right? The derivative of the bottom is minus 1.
What's the quotient?
What's the quotient rule? So this is a way of, if you wanted to find the derivative of something over something. It's a calculus derivative rule. If we had more time, we would prove it, but we don't have more time. Okay, good. Oh boy, what's this? It's not bad. What is it? Do those cancel? So what happens when I plug in 1? Get to. So math did not collapse. Very good. G prime of 1 is exactly equal to 2 over 1 squared. Great, so it agrees. So this works. This is actually a very clever way to nail it in one shot. Of course, the downside is we have to somehow derivative this thing. Okay? I'll say there's another way to achieve the same thing, which maybe I won't go into now. Another way to achieve the same thing is to study h of x, which is just, maybe I'll just write it down. Oh, let's just go over here and write something down. Okay. Don't worry, we're going to get to the punchline, which is this funny inverse tangent business too. Okay? Great. So now that we are over here, another way you could study the same thing is you could also let h of x equal to 1 plus x squared plus x cubed, and so on. Okay. I could always do this. And if this is easy. But what does this add up to? Now I can take the derivative of this guy. The derivative of this guy works out to 0 plus 1 plus 2x plus 3x squared plus 4x cubed, and so on. There's a mistake?
Oh, why can't you just use the quotient?
You can, but this is actually even easier somehow. Maybe not. Yeah.
Should that be 1 plus x?
1 plus.
No, 1 plus 2x.
No, I mean, please correct me. And if there's a mistake, please correct me. I think this is okay. But this guy, when you derivative this thing, you normally would get minus of 1 over the denominator squared, but the derivative of this is minus 1. Okay? So now I have this. And what do I actually want here? This is very close to what I want. Yeah?
We'll plug in x equals 1, so we actually get twice our desired sum.
So you said if x is 1,
X is 1/2.
X is 1/2, right? So what you can notice here, actually I can say you could even do one more thing. You could take this and join it with that one. You could do both, okay? So I'll say, yes, you're right, you could plug in 1/2. You can also actually merge it with this one. Both are possible. But at the end of the day, maybe just because of the time, at the end of the day, there are many ways to converge on this too, and I wanted to show you the calculus right. Okay, thank you. So now, just in the interest of time, I want to now move on to this strange number. What was that number? Something like inverse tan of 3/4 divided by pi. Okay? Okay. That's a pretty bad number, right? So before we go there, I'll actually say, when I was a high school student, I liked to do math contests. And I also, maybe I don't remember what year I was at this, but I was actually, how do you make 1/3 of the coin? I didn't think of doing this way. I was just like, well, you see, you could just get 3 different coins. Nickel, penny, quarter. You throw them up, and then you look at the order they land on the ground if you projected them onto some line. And so when they land, there's going to be some permutation of the 3, right? Then you think, how many permutations are there? 6. Great, and 3 divides by 6, right? So that's like another way to do it. Why did I say that? Well, I said that because that's like thinking outside the box, maybe. That's also why I didn't do different points. We'll actually do this a different way too, beyond what I'm going to say now. But I'm going to say when I give this talk at some places, I put a number here, and people actually came up with a way, thinking outside the box to do it. I actually will do this in a more serious way in a moment. But yeah, spin it.
So you construct.
So why 3/4?
So you can construct tan inverse of 3/4.
You can construct tan inverse of 3/4 by making 3 units here, 4 units here. Do people believe that I can construct this with a ruler and compass? Not ruler, straight edge and compass. Okay? You do this thing. Okay, you can do this. And then I guess you can draw this line. Great, so I know that angle. Yeah. Extend it like this.
Oh.
Somebody said, oh my. I get a marker, by the way. I have a coin. I have a marker.
If instead you at the
Atomic nail.
at the left side of
That's great. Okay.
the if you draw a semicircle
Draw a semicircle. You mean like this?
around with a radius of 5 from there.
Like this thing. This.
Yeah.
Yeah, okay. I have my coin.
And then you flip the coin.
Yeah.
You make the blackboard flat against the ground.
This will take a little bit more effort, but let's pretend we did that. Okay.
And then if it lands within the semicircle within that practical area, with the center,
But how do I know that when it lands, it really lands uniformly distributed on the plane?
you take the center of the coin.
Let's be very clear about this experiment. You said that rip this guy off the wall, put it on the ground. Okay, it's on the ground now. I've got my semicircle. I've got 3 centimeters. So I said we should say how to do this. So I've got this thing drawn in the sand. It's like Archimedes, right? So then you do something with the coin. You throw it in the air and it lands somewhere.
Yes.
How do I know that where it lands is uniformly distributed on the whole thing? Do you see what I'm getting at? It's like if it's slightly, if the way like the wind's blowing or something, slightly, not quite, but you're getting, like, people are getting close. Yeah.
Okay, so you have a full circle, and
full
then you have
circle.
those two. A full circle is radius 5, and then you have the 2 triangles within it. So, yeah, the same. Same triangles, and then you take your coin, you place it at this. You obviously take your board and put it on the ground.
Oh yeah, that's the first step. Yeah.
You take your coin, put it in the center, and you spin it. And assuming that the axis of rotation stays at the center.
Yeah.
Wherever it falls.
Yeah.
If it falls within.
Yeah. I understand what you're getting at. But this is good. There's a slight issue that you need to have these like massless strings and like unstretchable. Then you can actually do this for real. Like giving a hit like a marker. Yeah.
Well, if you get a spinning pedestal and you put
Yeah.
blackboard on the pedestal,
Yeah.
and you spin it.
And you forget the coin altogether. I understand. It's good. Yeah. So these are all good. In fact, let me just give it a hint. Okay, you think you can do this? I don't need the pedestal. This is my pedestal. Yeah.
Maybe mark 1 point on the coin.
Mark 1 point, like not the center. Yeah. Okay, I'll just say, let's draw a line through the center. That's basically what you're saying. Draw a line on my coin through the center. Now there's a line. I'm not going to mark up the coin. Actually, is that a felony? I'm not sure. Anyway, okay. So now I've got this line on the coin. Now what do I do? You can spin it. You can just like roll in somehow, and it'll roll enough time. It's not as tricky as the staying in the middle. Does it make sense? And then when it lands, somehow imagine this was the part. When it lands, it's like there. But there's a line through the coin that's doing something like this. Does this make sense? Yeah. And then when's my success?
The success when like the slope of that is in between the two lines.
So I thought this was a very clever solution. This is what somebody gave. Actually, whenever I give lectures or teach these hot note classes, I've learned something every single time. Because I come in, it's like, yes, I figured out this great way to do it. And then usually people blow your mind with something totally different, right? But I'm going to tell you, you don't need to do this. There's actually a way to do this purely with flipping the coin the normal way and looking at heads and tails. That's actually what I want to close on. You can actually get any real number you want. Any real number you want, just by flipping the coin. And now, in order to go in that direction, I want to slightly change one of the proposals that was here. Okay, that's why I said it's so valuable to have different ways to solve the problem. The first way to solve this is harder for me to generalize to arbitrary real numbers. The second proposal is easier. Actually, the third proposal, the one with the 2 flips. So let's talk about these 2 flips again. Okay. So let's go here. Great. So let's recall what was this algorithm. This two-flipping algorithm to get 1/3. There was a two-flipping algorithm saying first you do 2 flips. And then after you flip 2 times, there were some 4 outcomes. H, H. Which way were they? Do you remember? H, H
was disregarded.
Okay, so let me write it this way. H, 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 T, T, H, and T, T. T, T you said was disregarded?
Yeah.
So I'm going to write this. Is that okay? Does this make sense, what I'm doing here? Yeah. And now which one was win?
H.
This was win?
Yep.
And I guess these things are loose. Okay, so this works. I'm going to slightly muck around with what you wrote. I just feel like saying, that's when this guy is loose, and this guy is, again, go flip again. Do you agree that this still has probability 1/3?
Yeah.
Because it's the same. I just kind of change things around a little. All right. The next thing I'm going to do is I'm going to say, instead of using old school coins, let's use modern Bitcoin. Bitcoins are, how old is one? 1969. This is an old school coin. Awesome. Actually, this is pretty rare. Okay, way to go. Yeah, anyway. So Bitcoin, what am I making a joke, of course. I've never flipped a Bitcoin before, nor do I know what they look like on one side and the other. In fact, maybe they don't even have sides, but that was just supposed to be a joke. At the same time, I'm just going to pretend that, let's pretend that a Bitcoin has 2 sides, and the 2 sides are labeled not heads and tails, but they're labeled, what would you label a Bitcoin if you were supposed to do this? 0 and 1, you say. Okay, let's pretend that. So I got a new kind of coin. My new kind of coin, one side says 0, and the other side of the coin says 1. All right, none of these eagles or heads of famous presidents. So, okay, let's just mess around with this a little bit. HH, let's say, suppose I got 0, 0. Is that okay? I put my coin, I get 2 zeros. Flip this one. What should this one be if that was 0, 0? 0, 1. Okay. And now this guy is, and this guy, not 0, 0, 1, 1. Nothing happens so far. Do you agree that if I do this, it's still 1/3? Okay. Now I'm going to do more. I'm going to say, well, as I'm flipping all this stuff, I want to keep track of what I've done. Let's go here. This will fit. So I'm now flipping this Bitcoin in my merry way, and I have a certain way of just recording what I've done. I flip the coin, and I first start this record. I flip the coin, and I see a 0. And then I flip the coin again, and I see a 1. Oh, actually, that was an accident. But anyway, so sorry to do it again. Right? I flip the coin, give me a number. Not 2. Yeah, it's a 1. I hit 1. Okay, and then I do another one, and it's a 1. And unfortunately, you lose. Okay, not you, but suppose this happens. Then somehow you say you lose. Just for fun, I can't remember this. I have lots of these like strings of 0s and 1s. I just feel like putting dots in front of them. It's not this fast. And now hang your thought. Okay, I see the smile. So let's suppose I do it again. Oh, I get a 1. And then I do it again, I get a 1. Oh, that's not correct. Maybe what I do is I get a 0. And then I get a 1. And then I get a 0. And then I get a 0. Right?
Yes.
Okay. And then let's just like put one more random example. Like a 0, and then a 0, and then oh, I wish. Okay. Okay. These are kind of fun. At the same time, I'm going to ask you, who knows how to write the number 5 in binary? Why not? You said 101 is 5 in binary. Do people believe this? Okay. How many people know how to write the number 1/4 in binary? You're the base guy. Yeah. So 1/4 in binary is 0.01 because the way it's hard to read. Because the way the place value works, how much is this guy worth? 2 to the minus 1, and this is worth 2 to the minus 2. Okay. How do I write 1/3 in binary? Carefully. So that is true. You do need to do it carefully. But I think that there's something we've already done that was actually on this board somewhere that we can use. Your turn. Okay, yeah. Did you say a repeating decimal? You said 0.01, 01, 01, 01. What? But then this is right? Why is it? Because this is a quarter, a 16, a 64th. Have we seen this before? You used that earlier, right? Suppose I tell you I made a decimal that started with 0.0111 and there's like more stuff after it. Can you tell me how this one compares to 1/3? That decimal. I'm just telling you the first 4 digits of it. It's like some forever decimal. But I just showed you the first 4 digits. Can you tell me how it compares to 1/3? Back there.
It's more.
This thing is more than 1/3, and you're already so sure it's more than 1/3. Why?
Because instead of a 0, there's a 1 there.
Right here, something happened already.
Yeah.
Does it make sense? Right here, it already exceeded 1/3. It's like how you compare with place value. Does it make sense? This guy, how does that one compare with 1/3? Also more than 1/3. I'm sure, even if it keeps going, because the first one already failed. This guy here, how does this one compare to 1/3? It's less than 1/3. And this guy here is less than 1/3. That's interesting. So I have my algorithm, which I mucked around with, and somehow it maps to looking at my strings of h's and t's, turning them into zeros and ones, and comparing the resulting decimal with 1/3. So actually, let's go back to something I said way back at the beginning. How do you generate a random number between 0 and 1? Suppose, we'll read this again without the grand finale in some sense. Suppose I just wanted something very different. I'm not asking about any of this, this particular coin flip thing. And you have a computer. Suppose you have a computer and you want to make a random number between 0 and 1. What would you do? Random.org. But if you just have one source of bit, like one bit of randomness, then you keep doing, you
Make those digits in binary by hitting the button for your entire.
Does this make sense? What I'm trying to say is that what you do is you write point, and then you flip, meaning you get 0 or 1. And then you flip again, and you get 0 or 1. And you do this forever. The outcome is a uniformly random. Do you agree that it's uniformly random, meaning that it's distributed equally on the whole 0, 1 line? The way you can, the uniformly random number in 0, 1. Yeah, okay, let's put it this way. Okay? And the reason it's distributed uniformly is because here's 0, here's 1. What does your first flip actually tell you? It tells you something nice. If I get a 0 or 1, it tells me, this is like a guess your number game. The very first thing cuts the space exactly in half, right? And it tells me if it's 0 is there and 1 is there. And the second flip, suppose it was this one. The second flip cuts it. Does this make sense? So you end up evenly distributed over here. Great. What if I just tell you some other problem, saying the probability that if I take a uniform random number in 0, 1, that it's the probability that this uniform number in 0, 1 is less than 1/3. What is this probability? 1/3, exactly. Does that make sense? Because here's this, here's 1/3. What's the chance of this here? Exactly 1/3. What if I put this sign here? Also. No difference, because the chance that you get exactly 1/3 is 0. Okay, what does this have to do with my Bitcoin flipping?
So you flip a coin until you get a string of numbers such that no matter what the next digits are, it will stay less than or greater than.
So you're giving a brand new algorithm, not about flipping in pairs anymore. Now you're just going to flip 1 at a time. Okay, here's a new algorithm, a new way, a fourth way to get 1/3. To get 1/3, another thing you can do now is you just flip coins one after another. So, or the same one many times, whatever, however you want to say it. It's just keep flipping 1 time forever. And record your decimal, so to speak, 0, 1, 1, whatever. And then you want to compare with this 1/3.
Yeah.
Right? So what you've actually done is you've converted 1/3 to binary. Right? And then you compare this with this. And if it's less, as soon as you know it's less, you say win. As soon as it's more, you say lose. And it's never equal. So now how do I do this with this horrible random number? Like if I have some very strange real number, what do I do to this algorithm? Remove the 1/3 and put whatever you want. Does this make sense? So at this point, you now know how to use an innocent coin to get any probability of success between 0 and 1. And this is pretty neat. Of course, you can do other very clever things using the physics, but this is what I want to share. And actually, that basically brings to the 1 hour. So thanks everyone for staying up.